The integral of sine x over x, taken across the whole real line, equals pi. 3 proofs, no shared trick between them. This is the integrand, sine x over x. The area under it is pi, and there's no elementary antiderivative to reach that number directly. Each proof reaches pi through a different detour, a parameter family, a contour in the complex plane, or a Fourier inversion. The integrand has no elementary antiderivative, so a direct attack is off the table. A standard escape is to introduce a parameter, embed the integral we want into a family, make the family differentiable in that parameter, and compute the derivative instead. The exponential factor is the natural damping choice. It forces convergence at infinity for every positive t, and it recovers the integrand we care about as t goes to 0. Connect the two endpoints by differentiating under the integral. The derivative pulls down a minus x from the exponential, which cancels the x in the denominator. What's left is the Laplace transform of sine, and the Laplace transform of sine is 1 over 1 plus t squared. The derivative of I is in closed form, even though I itself is not. Integrate the derivative from t up to infinity, using that I vanishes at infinity. The antiderivative of 1 over 1 plus t squared is arctan, so I of t reads as pi over 2 minus arctan t. Send t to 0. The arctan term is gone, so I at 0 is pi over 2, which is half of what we want. Double it by even symmetry. The integral across the real line is pi. Sine x is the imaginary part of e to the ix. Lift the problem to a complex integral, e to the iz divided by z, a function with a single simple pole at the origin. That's the kind of function contour integration is built for. Build a closed contour in the upper half plane, the real line from minus r to r, a small semicircle that steps around the pole at 0, and a large semicircle closing everything up top. No poles sit inside. By Cauchy, the integral around the whole contour is 0. Let r grow. On the large semicircle, e to the iz decays fast enough that the whole arc contribution vanishes. That's Jordan's lemma. Shrink the small arc. It sweeps a half circle clockwise around a simple pole, so it contributes minus I pi times the residue of e to the iz over z at 0. The residue is 1. Put the pieces together. The big arc is 0, the small arc is minus I pi, and the sum of everything is 0. So the two real segments, merged into a principal value integral, must equal I pi. Take imaginary parts of both sides. The cosine contribution is an odd function, integrated symmetrically, so it drops out, and the sine part reads the integral we started with. The integrand has the shape of a Fourier transform. That's the hint. Pick a function whose transform is sine x over x and read the integral as a Fourier evaluation at the origin. Take f to be the indicator of the interval from -1 to 1, a rectangle of width 2 and height 1. Its Fourier transform is a single integral, and the antiderivative is elementary. Antidifferentiate in t. Evaluate at the endpoints. The numerator is e to the ixi minus e to the minus ixi, which is 2I times sine psi. So the transform of a rectangle is a sphinx, plotted on the same frequency axis, and you can see the duality. Fourier inversion says the value of f at a point t equals 1 over 2 pi times the integral of its transform against e to the ixit. Evaluate both sides at t equals 0, and the exponential becomes 1. The rectangle at 0 is 1. Its transform is 2 sine psi over xi. Plug both in, move the 2 pi over. The Dirichlet integral equals pi. 3 independent proofs: a real variable parameter derivative, a complex variable contour, and a Fourier inversion at the origin. Each lands on the same pi, same value every time. The Dirichlet integral: 3 ways, 1 answer.